Let's explore just a little bit how the equilibrium constant is related to the position of equilibrium and especially how the changing position of the equilibrium is related to the equilibrium constant. So you may remember that if we have an equilibrium constant Kc, for example, of 1, that means we have gone basically halfway. We're in balance. The reactants and the products are half and half, essentially. When you put products over reactants in your Kc expression, you end up with 1. We have the same number on the top and the bottom of the fraction. If we go below 1 times 10 to the minus 2, essentially we say that the equilibrium is pretty much shifted to the left-hand side. You can go below there, you can go a long way below there, but anything less than 1 times 10 to the minus 2, it's certainly fairly well shifted over to the left-hand side. So most of what you have in the reaction mixture there is your reactants. On the other side, 1 times 10 to the 2, you have mostly products in your reaction mixture. Okay, so let's have a look at some equilibria, and I'm using data that I found for 298 Kelvin, which is a warm room temperature, should we say, 25 degrees. So if we have a look at some examples, this equilibrium here, the equilibrium between NO2 and N2O4, if we express it like this, has a Kc value of 6.1 times 10 to the minus 3. That actually has a unit of moles per decimeter cubed. I've left the units off these numbers. I'm just interested in the numbers really here. Here on the other side, our Kc here, we have a 794. That's the other way. We have the equilibrium between hydrogen and iodine gas, and that's actually got no units at all. So have a look at the NO2 formation. You can see that from that equilibrium constant, 6.1 times 10 to the minus 3, most of what you'd have in your reaction mixture is going to be N2O4, because the equilibrium is shifted well over to the left. On the other side, the hydrogen and iodine, we have a Kc value which is larger than 1 times 10 to the 2, and so therefore we say that that's shifted to the right hand side. You have an awful lot of Hi in your mixture and not much H2 and I2. Let's just have a look at this graph. First of all, the top graph, you can see I've put K up the y-axis and time across the x-axis. I'm saying here, as the reaction goes on, what happens to K? What's K? Well, I've used sulfur trioxide formation, and I've put the equilibrium expression there. You can see I've got a Kc expression for what happens when we put SO2 and O2 gases together and react them to form SO3. We end up with this expression for Kc. Now, K is actually the same expression. Kc is only applied at equilibrium. Okay, so that doesn't mean that this proportion can't ever change. It does, because obviously if you dump a load of extra chemical in, your proportion is going to change, and I'm going to call that K. So K is the same as Kc. You can see I've just changed that expression there sneakily. So down on the bottom, you can see that I've got, and this is not to scale, my SO2 concentration and my SO3 concentration on my graph at the bottom. Okay, and what I'm going to do is I'm going to put a stressor onto this equilibrium, which means that I'm going to change something, and what I'm going to change is the concentration of SO2. I'm going to raise the concentration of SO2. Now at this point, you can see that the K value, okay, if I put my Kc expression and I put the numbers in, I will not get Kc at the moment because I've got a lot more SO2 than I should have. And that means that the bottom half of the fraction is going to be larger, which means that the K value, or is going to be less than Kc. Okay, at the same time as the SO2 is going up. So what happens now? Well, you'll remember that concentration is related to reaction rate, and you'll remember that an equilibrium is when the forwards and backwards rates are equal. increasing the concentration of something increases the reaction rate. And so the rate that SO2 and O2 react is going to speed up because we have a higher concentration of SO2. And that's going to continue until we've made enough product for the reverse reaction rate to speed up to the same amount. Okay, so essentially we are using up SO2, and as we use that, the reaction rate forward slows down, and we are producing SO3. And as we do that, the reaction rate reverse speeds up, and when they equal each other out, we end up in equilibrium again. As we're using up SO2 and increasing SO3, the K value here is going to go up because we're increasing the number above on the top of the fraction and we're decreasing the number at the bottom of the fraction. So we can show that on the graph like this. You see, we start with the K value not being equal to Kc, and as SO2 is used up and as SO3 is produced, we get closer and closer back to that magic ratio of Kc. And when we reach a value of Kc, we say we have reached equilibrium. And so when we've increased the concentration of SO2, which is a reactant, okay, we can say that the equilibrium has shifted to the right, because when we increased the SO2, we ended up with a value for the equilibrium constant which was less than Kc should be. And so we've gone from a lower number to a higher number, which means on my original number line we would have been going to the right. So an increase in concentration of the reactant shifts the equilibrium from this point here, where the Kc value is has been changed by the increase in concentration down here. From here to here, we have shifted to the right. Similar idea. If I increase the concentration of SO3 this time, you can see that now the number on the top of the fraction is going to be much larger than the number on the bottom of the fraction. And so therefore we are going to change our value of K to be much larger than Kc was. And so from this point, we're going to use up SO3 and make SO2 and O2. So the quantity of SO3 is going to go down from this peak that I've just put on here, and the quantity of SO2 is going to raise. And as that happens, the number related to K is going to get smaller and smaller because there is less of the number on the top and more of the number on the bottom, and we'll end up reducing the number K all the way back down until we get to the point where we're once more at K equals Kc, equilibrium. Okay, so the equilibrium expression is only Kc at equilibrium.